Not yet.
Okay.
Maybe reshare again.
Okay, let's see. New share. Oh. Share. No. Can you see it?
Still loading. How about others? Đăng, Phương.
Let me share the entire screen.
No, I still don't see anything.
Okay, good now.
No,
now.
it show up now.
Okay, then to get started, so because our themes today, our themes is on adversarial robustness of VL language, vision language model. So I will go through the adversarial robustness definition first. So robustness analysis evaluates the performance of the model under different conditions and perturbations. So in the study that we discussed in the last session, we can see the results of the robustness of the adaptation method on some vision language tasks. So here we have image corruption and text corruption with different adaptation method, like from multiple adapters or high performance or compact or low rank adaptation. So you can see in this table, the single prompt, only like 2% param is updated. Or multiple prompt is only 4% param updated, which indicates that it's a significant. These are significantly lower compared to other methods from like full fine tuning 100%, multiple adapter 12%, and multiple LoRa with 7% Yeah. So
can you explain a little bit more about this table? What is it about?
So this is the clean performance and relative robustness. Like you can see the accuracy and the relative robustness on of adaptation method based on like clip part image with like some image corruption, like we add noise to the image, or text corruption, we add like perform some text perturbation, like changing positions or duplicating characters, etc. And we get the we calculate the performance of the clipboard model against these adversarial attack. So we have the number of parameters updated and the accuracy across these data sets. Is it clear to you?
Okay, but what is the main message of this table?
So just a introduction that PROM require updating a significantly more smaller number of params compared to others methods. So this makes PROM highly efficient and suitable for scenarios where computational resources are limited or where rapid adaptation is needed. So due to fewer param updated, PROM can be easily adapted to different tasks without the need of extensive retraining. So this flexibility is advantageous in real world application. So that's why I choose PROM engineering on foundation model as our today's main theme on the seminar. Just that's all. That's the main idea when I like you can see the performance of like prompt is like trade-off between the robustness and like why there's the trade-off between the efficiency of prompt and the reduced performance of the accuracy and the robustness of prompt compared to more param-intensive methods. So we can consider prompt for like more suitable tasks that do not really that needs the trade-off between the efficiency and the performance. That's the idea.
Okay.
So about the prompt, we have so we first go through the problem. Secondly, we go to the prompting methods from for image text matching, multimodal to text, and text image generation with different like scenario, and we will move to the prompting LVM and Uni model that I will cover later because that's we may not have enough time to cover this part. That's just some comparison between the prompting for multimodal and unimodal. And for the last section will be the challenge and opportunities. So the main task, we would have multimodal to text generation and image text matching. So for three types of and text to image generation, of course, we have three types of vision language models, multimodal to text generation models. One represent of it is the Flamingo. The second one is the image text matching. One representation is Clip. And the last one, text to image generation model, we have Stable Diffusion. So here we investigate the prompt engineering on three types, and which are like we categorize existing prompt engineering approach from an encoder and decoder perspective, like from figure 1, this figure, and the prompt can be added into the encoder side or the decoder side. So as I stated earlier, this is a multimodal to text generation. This is the training paradigm from Flamingo. This one from Clip, and this one from Stable Diffusion. Okay. So for more for more fine-grained, we can have the text prompting. We can prompt from the texture module. We can prompt from the visual and from them jointly with a image text matching loss. Yeah. So prompt engineering, like for more precise, is a approach to adapt the large pre-trained model, also known as a foundation model, to new tasks by augmenting the model input with task-specific hints. So the model input is augmented by additional part called prompt, which could be manually like create the language instruction or generate language instruction or automate the generate vector representation. We have two key types of prompt. You can have hard prompt or soft prompt. if the hints are like human interpretable in natural language, we can call it hard prompt. In some studies they refer to it as in context learning. They enable the model to learn from task instructions, or few short learning with some demonstration or supporting some information in the context. So other way is like soft prompt. The hint could be in continuous vector representation and optimize prompt directly in the embedding space of the model. So we classify prompting method like more to be more frequent. We have further divided into subcategories. Like in hard prompt, we have task instruction, in context learning, or retrieval based prompting, or chain of thought. Soft prompt on the other hand are like continuous vectors that can be fine-tuned using gradient methods. Yeah. So some methods such as p-tuning or rowing adaptation, they introduce additional module into the model. Like for this one, the model architectures are kept kept separately, and we don't like really change the model architecture, which means it's kind of black box, I guess. So it will different from that two methods, from p-tuning and lowering adaptation. So for hard prompt, we can involve the use of the carefully designed prompts that provide explicit task-related instruction to guide the model's behavior. So I can use a text edit or some notes here. So the formulation of this method can be presented as the X input can be represented at H xt, where here H serves as the task instruction function. So take the image and take as input and produce the model input the representation X input. So X will be the image and T will be the text. So the in context learning is the method where the model is exposed to a sequence of related examples or prompts, which enable it to learn and generalize from the provided context. So the in-context learning method can be represented when we add the context here. The context is given with the image and text input. The resulting modified input representation can like capture the model's understanding of the context and used to generate coherent and contextually relevant responses. So by exposing the model to a sentence or a related example prompts, the in-context learning method like promotes the performance in understanding and generating the response. Yeah, so that is the in-context learning. So we have others like retrieval-based prompting, like it's a method that involves selecting prompts or context using retrieval techniques. So in this approach, the model retrieve relevant prompts or context from a pool of prompts or external knowledge base to guide its generation or decision-making process. So the retrieval base prompting method can be denoted by the formulation, like we can have the C equals to retrieval xt. So in this formula, we can have the retrieval method R that get the prompt or context based on the image X and text T inputs, and then the context will be used to guide the model to generate or the output.
On question, man. So if you have both text and images, what would be, so the retrieval model here is for image or for text, or they have for both?
For example, here we let me see for here we can use like, let me get an example for you to easier for understand. Here.
Yeah, and by the way, we are not seeing
can
the
use-
screen that you are talking about. We are
no.
seeing we're seeing your slide.
Okay. Let me bring it to you here. It's hidden, so let's see slides to see all the slides. Here.
Mhm.
So you have a image. So question what is the warming outdoor temperature at which this kind of weather can happen. So we can change like from the image we can have the textual description, like people are standing in a parking lot with some umbrella as is known, and then we prompt the question image textual description to the GPT-3, for example, and then you get the implicit knowledge from the image texture description, and then you will get the answer. So this by not learning the visual embedding, instead it converts the image to texture description and query GPT-3 directly to predict the answer to leverage the future ability of GPT-3. Yeah, that is an example of retrieval-based prompting.
Oh, wait. Sorry. That's not retrieval, right? Because you need to, I mean, in retrieval base, you probably need to have a retrieval model, right? Where you, let's say, if I have one image,
When it's query the GPT-3, it can be considered as like retrieve the hidden knowledge from GPT-3. Other method we can see it's let me see here, where is it?
for example, right, with the Q&A, the visual Q&A example just now, I can try to look into the data that like whether they have similar questions or similar example that you already know the answers. So that's, to me, is an example of a retrieval-based prompting, right? Where you, like, let's say you don't know the answer for this particular image and questions, but then you can look into the database and see what are the similar images or what are the similar questions that already have the answers. And then I look into those examples as part of my context, right? And then I will try to generate the answers. So to me, is what is called retrieval based, right? Because you actually need to do some sort of similarities search or retrieval to find what they call like similar cases or similar relevant context for your original questions.
Yes, that can be. Let me see. Here I'm thinking of it as the the hidden knowledge can be like when we have the knowledge from LM as the like the lowest temperature that we can stand. That is the way I thought of as the retrieval base. We can also think of retrieval base as that's kind of data that we can query the knowledge, external knowledge. For example, the Wikipedia or something like that, like to query with the description as to like answer directly the question. That is one way to perform retrieval based prompting. Like, okay, I think it makes sense though.
Yeah, I mean, we have to be clear about what is this that we call retrieval-based prompting, right? So it's part of the in-context learning, but the context is the result of a retrieval model.
Yeah.
Yeah, and then you use a context with the original prompt to create new prompt and querying the vision language model, right? So actually back to my question earlier, now you have both image and text, right? What would be your retrieval model now? Because you can either retrieve based on the image or you can retrieve based on the text.
Yeah, currently what I'm thinking of is like we have the text in like we have mostly we have the texture description of the image. One way is to use the vector representation, like we can find the similarity scores or something like that in the knowledge base and retrieve the what we want from that and use it as the context to prompt the LM to generate the answer. Other ways I'm thinking of like also using similarity score for like text for image, but I haven't seen any web that have done that before. So that remains like a question. But text probably text query probably one like popular way that people do to like retrieve the context in the to input in the what we said earlier, like the context here, the context here.
Okay.
So the last one is the chain of thought prompting. So it's a method where the model is prompted with a series of instructions or questions that progressively build upon each other. So the each prompt is a chain add to context or to narrow down the focus, add to the context, or they narrow down the focus, either of them. So that will like enable the model to generate more coherent and contextually appropriate responses, because large language model have some limitation on the context length. So in a train of thought will like one of the ways for us to improve that. So this method helps the model to maintain a logical chain throughout the conversation. The like we have others hard prompt method, but for the train of thought we don't really have the specific equation. It's more like the intuitive approach, iterative process of applying the prompt. So each step in the training, the model, like here, I will have a note here. So we have the step step I. So each step of a train, the model will respond from previous prompt that is used as input for the next prompt. So the I plus 1 is used is from ti xt. Here t represent the prompt function that take the image x and t and input and as input and generate the response. So the output of the I prompt denotes as the txi serve as the input for the ti plus 1 prompt. So by progressively building upon the previous prompt, the iterative nature of the Turing programming method can help the model to be more like coherent and generate respond like align with the evolving context of the conversation.
So this chain of thought is a one way to improving the reasoning capability of the large language models, right?
Yeah, it's also the
How about the
logical. Yeah.
How about the vision language models? What is the equivalence of train of thought for vision language model prompting?
I think it's still based on the context because basically chain of thought is used to like maintain the logical expression of the conversation. So
What I mean is, and so you have language model, right? And your train of thoughts would be a sequence of, or it could be the rationale that you ask the model to actually produce, and then use it as a part of the next prompt. But what is this that we call maybe train of thought prompting for vision language model? You know, like I'm trying to differentiate. Is any difference between when you do train of thought prompting with large language model and when you do train of thought prompting for large vision language model? Is there any difference?
I think there's not many experience because it's just a iterative process, and the difference is just we import the text in it. Because basically it's still a hard prompt, and the mechanism here is to generate a train of like a plan to generate the prompt, the context for the input to generate the more correct answer. So I think that there's not quite very many different between the chain of thought in language only and the vision language. Not clear?
Actually, the chain of thought prompting in vision language model. So you give a prompt with a context and including the image in it, and then you prompt another context with an image and ask about that image specifically. So as I have delivered on my previous seminar, like if you gave a model like a picture of a resident, for example, and you talk about his hobbies, and then you give another image about some famous people, and then you ask about the hobbies, and it will turn to you the similar answer in the context you have given, and that can be think as a chain of thought prompting in large reason language model. It is not only about the text prompting. Is you can include the image, and I have mentioned about the data, the technique called data leaving, interleave the data, which means you train the model with uh, 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 with such kinds of data from like that, like the question will be a text and plus the token that indicate the image, and then you ask a question with another image token, and that's kind of data they train to get the chain of thought prompting make to
I think it's better you present that paper next week.
actually I have present once in my first seminar, if you remember. I have showed that or maybe tomorrow I will talk about it a bit. Yeah.
Okay, then move on, please.
Okay. So, unlike hard prompt, we have soft prompt. So soft prompt are like continuous vectors that can be fine-tuned using gradient-based method. So, for example, this process might involve concatenating a learnable vector with the input embeddings and subsequently optimizing these to align with a particular dataset. So soft prompt can be classified according to whether new token internally incorporate within the model architecture or simply attached to the input. So here we can see so one representation of it, it's prompt tuning. Sorry, this one, not this one. I didn't include the prompt tuning slide here, but basically it just create continuous vector representation as input hints. So during the training process, the model learned to refine the prompt, so it to improve its performance on specific tasks. So enable the model to dynamically generate effective prompts based on its understanding of the task. So I can write some expression here for you to easy understanding. So we have a prompt parameter xp. We have the input x input and the y as the y e and this denotes the generated previously generated output, and the x input is the modified input that based on the prompt. So the training objective will be like we have to minimize the loss function that with the model output giving the this is the here and provided the e output we generated and the input X input. So here we aim to minimize the loss function where f x xc xp represent the model's output given the prompting parameter xp. So the objective from tuning is to minimize the loss function between the model's output and the desired output. So given the previously generated output and the modified input, so by continuously refining the prompt through prompt tuning, the model can adapt its behavior and improve its performance on tasks, on decision tasks. So the dynamic generation of the effective prompt based on the model understandings will to enhance the model to generate accurate and contextually relevant responses. So instead of using hard prompt, we can use soft prompt. That is prompt tuning. Other methods is prefix prompt tuning. It's quite similar to the prompt tuning. It's only like adds some task specific vectors to the tasks, to the input. In this case, these are, but in this case, these vectors are inserted in like all layers of the model and can be trained and updated independently while keeping the rest of the pre-trained model parameters frozen. I do have some. Where is it? I can find it. I can give it to you later. But basically, the prefix tuning is will add some as a specific token that it's task specific. So that is the idea of soft prompt. It's just add some vector representation to the input and try to optimize that to obtain the best performance of the model without having to retrain the huge model with lots of parameters. So this one is the initially that the plan of mine is just to go through the hard prompt and soft prompt title and then go to specific. So this one is the example of the hard prompt, representation of using hard prompt to train the vision language model. So you can see it quite like frequent. It's clip model. So it create the dataset classifier from the label text. So they add a photo of an object, which before the input for captioning tasks. So that is one way for them to use hard prompt for training the clip. And nowadays, clip VIT is one of the most common use in text in visual encoder. So their idea is really simple, to add some prompt to add some like more prompt in the texture caption of the image, and give us a really powerful model like clip VIT was one of the most common image encoder. So I will go through some advances in prompting techniques for vision language model. So you can see here, like because nowadays, like we have transformer is one of the most powerful architecture like commonly used. So model will in multimodality scenario, as I have mentioned in the first session, model will be divided into two main types based on their fusion module. So module utilizing an encoder and decoder as a fusion model, and other model employing a decoder only as the fusion module. So so here we have an example of prompting model with encoder and decoder as the fusion module. So the representation is the VLT5, and they use text prefixes as prompt. For example, like VQA is used for question answering. Here we use like visual grounding or caption in the image captioning task. That is the way used to use text prefixes as prompt. They also use like visual token like this one, this two, this three, to share like to specify corresponding like image region of interest, which is kind of, I can say that is one kind of prompting the visual for the VLT5. So they use the caption region like this visual eye to the grounded captioning task, that which this will indicate the model which should generate caption based on the specific visual suggestion. Like here, they input the this tree here. That is the one representation of